Hello friends, in this video we're going to be discussing chapter 31, Faraday's Law. This chapter explores the effects produced by magnetic fields that vary in time. In this chapter we're going to discuss Faraday's law of induction, motional EMF, Lenz's law, induced EMF and electric fields, generators and motors, and eddy currents. In the first section, we're going to discuss Faraday's law of induction. Through Faraday's experiments, he was able to conclude that an electric current can be induced in a loop by changing the magnetic field. The induced current exists only while the magnetic field through the loop is changing. This graphic is a simple experiment showing that the current is induced in a loop when a magnet is moved towards, away from, or is stationary in respect to the loop. In general, the EMF induced is directly proportional to the time rate of change of the magnetic flux through the loop. This is known as Faraday's law of induction, which can be written as shown below, where the magnetic flux through the loop is over time. Furthermore, if a coil consists of n number of loops of the same area, then you would include the number of loops into the law of induction. In the next section, we are going to discuss motional EMF. We are going to describe motional EMF as the EMF induced in a conductor moving through a constant magnetic field. From the magnetic version of the particle in a field model, the electrons in the graphic of this conductor experience a force equal to Q times V cross B, which is directed along the length of L and perpendicular to both V and B. Under the influence of this force, the electrons move to the lower end of the conductor and accumulate there, leaving a net positive charge at the upper end. As a result of this charge separation, an electric field is produced inside the conductor, which can be expressed in the simplified form as E equals V times B. Looking at this graphic again, we can say that L times X is the area enclosed by the circuit, where L is the length and X is the position along the bars. With that being said, the magnetic flux through that area is equal to BLX. With the formula for magnetic flux, we are able to consider Faraday's law of induction and manipulate the equations together, noting that X changes with time at a rate dx over dt. It equals V, which allows us to find the induced motional EMF. In the next section, we will discuss Lenz's law. Lenz's law indicates that the induced current in a loop is in the direction that creates a magnetic field that opposes the change in magnetic flux through the area enclosed by the loop. In other words, the induced current tends to keep the original magnetic flux through the loop from charging. Looking at a similar graphic as before, Lenz's law states that the induced current must be directed so that the magnetic field it produces opposes the change in external magnetic flux. This is because the magnetic flux due to an external field directed into the page is increasing, aka the induced current must produce a field directed out of the page. In this section, we will be talking about induced EMF and electric fields. Looking at this graphic, we have a loop of radius r placed in a uniform magnetic field that's perpendicular to the plane of the loop. If the magnetic field changes with time, an EMF, according to Faraday's law, is induced in the loop. The induction of a current in the loop implies the presence of an induced electric field E, which must be tangent to the loop because that's the direction in which the charges in the wire move in response to the electric force. The work done by the electric field in moving a charge Q once around the loop is equal to charge times EMF, and since electric force acting on the charge is charge times the electric field, the work done by the electric field in moving the charge around once the loop is charge times electric field times the circumference of the loop. These two expressions for work must be equal. The EMF for any closed path can be expressed as the line integral of E times ds. Therefore, Faraday's law of induction can be written in this general form. In this section, we are going to discuss generators and motors. An alternating current, or AC generator, consists of a loop wire rotated by some external means in a magnetic field, such as our graphic depicts. As the loop rotates in a magnetic field, the magnetic flux through the area enclosed by the loop changes with time, and this change induces an EMF and a current in the loop. The ends of the loop are connected to slip rings that rotate with the loop, and the connections from these slip rings act as output terminals for the generator. And these go to the external circuit that are made by stationary metallic brushes in contact with the slip rings. The magnetic flux through the coil at any time is equal to B times A cosine the angular velocity times time. Furthermore, the induced EMF in the coil is equal to the number of turns times B times A sine angular velocity times time. Continuing on, we're going to briefly touch on direct current, or DC generators, and motors. A DC generator is essentially the same as an AC generator, except that the contacts to the rotating coil are made using a split ring called a commutator. A motor is a device into which energy is transferred by electrical transmission, while energy is transferred out by work. Essentially, a generator operating in reverse. So for the last section, we will discuss eddy currents. As we've seen, an EMF and a current are induced in a circuit by a changing magnetic flux. In the same manner, circulating currents, called eddy currents, are induced in bulk pieces of metal moving through a magnetic field. This phenomenon can be demonstrated through the graphic here on the screen. In the graphic, we have a flat copper or aluminum plate attached to the end of a rigid bar that swings back and forth through a magnetic field. As the plate enters the field, the changing magnetic flux induces an EMF in the plate, which in turn causes the free electrons in the plate to move, producing the swirling eddy currents. According to Lenz's law, the direction of the eddy currents is such that they create magnetic fields that oppose the change that causes the currents. For this reason, eddy currents must produce effective magnetic pulls on the plate, which are repelled by the pulls of the magnet. To read more about eddy currents, see pages 953 to 955 in Survey and Jewett's Physics for Scientists and Engineers. And that concludes it for the discussion on Chapter 31. Thanks for making it this far in my review of Faraday's Law. And as always, if you like the content that you saw in this video, don't be afraid to drop a like down below. And don't forget to hit that subscribe button to never miss one of my future videos. See you all next week.